In this video, we will take a look at protocol mechanisms for safe data transfer. The aim is to preserve the order of data frames and to deliver each frame exactly once to the application, that is, to avoid loss and also not to provide it several times. Real media do not fulfill these aims because they are unreliable. Therefore, protocol mechanisms have to be used. In the following, there is a general scenario. We have an end system A that wants to send a data stream to an end system B. Its layer 2 gets a certain amount of data according to the conditions for minimum and maximum payload sizes. On layer 2, additional control data is added, and then the data unit is provided to layer 1, which actually transmits it. On layer 1, bit errors may happen, which is detected on reception so that the frame is discarded in this case. In addition, frames can get lost. A simple protocol is a stop and wait protocol. End system A sends a data frame and waits for a confirmation frame. Once it gets this acknowledgement frame, it continues to send data. If there are, for instance, internal processing delays on the receiver side, then this delays the acknowledgement and influences the efficiency. Therefore, it is better to have a separate reception unit. On this slide, we can see the effects of frame loss. The data frame can get lost, but also the acknowledgement frame. Without modifying the stop and wait protocol, the transmission would not continue. Therefore, it is necessary to introduce timers. This means the end system A starts a timer when sending a frame, which is indicated on the slide by a clock symbol. The time is an expectation how long it can take in the worst case until the acknowledgement is received. So, if there is no acknowledgement, then the frame will be resent. Now a new difficulty can be present. The sender cannot distinguish whether the data frame or the acknowledgement has been lost. In both cases, the sender does not get an acknowledgement. Let us assume that the acknowledgement has been lost. Then the sender repeats the data transfer and the data frame is received again by end system B. Here it is necessary to recognize that it is a duplicate. Otherwise, its payload would be delivered to the application twice. The solution is the introduction of sequence numbers. For the stop and wait protocol, just alternating numbers 0 and 1 are sufficient. With the alternating sequence numbers, it is possible to identify the duplicate. Please note that it is necessary to confirm the reception of the duplicate, otherwise it would be repeated again. We make a rough calculation on how efficient the stop and wait protocol is. The realistic assumptions are that the signal runtime is 10 milliseconds, the bitrate may reach 1 gigabit per second, and the frame size is 1500 bytes. In addition, potential frame loss is ignored. Then we can transfer 1500 bytes successfully every 20 milliseconds when considering the acknowledgement. At the end, as you can see, the efficiency is just 0.06%. That is, most of the time the sender waits for a confirmation. In order to improve the situation, it is necessary to send several frames quickly after each other. This can be implemented by the credit method. According to this method, a sender can send a predefined number of frames without waiting for a confirmation. Then the sender has to wait for the confirmation and afterwards sends again this number of frames. However, there are still times where the sender stops to transmit. A further improvement is the sliding window method. In the sliding window method, the sender has a credit which is decreased on frame transmission but is increased on acknowledgement frame reception. Let us assume the initial credit is 10 frames. If the sender sends 7 frames and has received confirmations for the first 2 frames, then the current credit is 10 minus 7 plus 2 equals 5. So the sender can send 5 more frames if it does not receive a confirmation until then. In the best case, the sender continuously gets confirmations and therefore never has to stop transmitting further frames. As a side remark, dynamically adapted window sizes are possible, which is however more relevant for the OSI layer 4. When sending several frames without waiting for confirmations, frames in the middle may get lost. The question is how to deal with this situation and in particular how to confirm that a part of the frames has been received and some other part has been lost. There are 2 main options, go back N and selective repeat. In the go back N method, the confirmation just relates to the last frame where everything was still fine. This frame is confirmed so that all following frames are retransmitted. This implies that also frames which had arrived without problems are retransmitted. In the selective repeat method, only those frames which have actually been lost are retransmitted. This method requires a modification of the acknowledgement to indicate the partial loss. So when we compare both methods, we can conclude that go back N is easier to handle for the receiver side. However, selective repeat avoids unnecessary retransmits and potential errors in these retransmits. Due to fewer retransmits, the medium may then also be available for other data transfers.